We know that there will be some loss of energy in case two objects are hitting each other and it's not a perfectly elastic collision. And the loss of energy can be actually calculated pretty easily. You have two objects. Let's say you have object A, which is traveling initially with a velocity UA, and then there is object B that is ahead of it traveling with some velocity UB. You can find out the initial velocities, you can find out the initial KE of A and KE of B, and you can add them up to get the total KE of the system initially. So let us say A has a mass MA. So if A has a mass MA and if B has a mass MB, then I can find out the total KE initial. KE initial is going to be half MA UA square plus half MB UB square. And after the collision, these two objects will be traveling with velocities VA and VB. So here you have object A traveling with VA, and then you have object B traveling with the VB, and you can figure out what is the total energy, kinetic energy of these two objects after the collision. So you can find out something called KE final, which is half MA VA square plus half MB VB square. And then all you have to do is to find out how much is the loss in kinetic energy. You have to find out KE initial minus KE final. So this is easier said than done. The reason being that VA and VB are both big functions of U and UB. If I recall right, then the expressions for VA and VB were, VA was MA UA plus MB UB plus I think there was MB into E times UB minus UA divided by MA plus MB. And there was an analogous expression for VB, but before we go for that, let's have a look whether this is right or not. Yeah, it is right, no? Yeah, cool. So that memorization trick works. And then we have a similar huge expression for VB. VB is in fact MA UA plus MB UB plus, now here instead of MB we have MA into E into UA minus UB divided by MA plus MB. So this is the entire expression for VA, this is the entire expression for VB, and you have to substitute these two here in VA square and VB square. You know just by having a look at these expressions that it's going to be huge. So we don't want to do that. What we want to do although is to find out the maximum loss of kinetic energy, and that is an easy thing to do because for maximum loss we are talking about a completely inelastic collision, and for a completely inelastic collision this guy E will be 0. So the moment you put E is equal to 0, this third term in the numerator here in the expression for VA and in the numerator here in the expression for VB will go off, and we will get a slightly simplified expression for VA and VB, which we are going to insert here and get the final answer. So for a completely inelastic collision, you will have loss in kinetic energy is equal to half MA UA square plus half MB UB square minus half MA plus MB into MA UA plus MB UB divided by MA plus MB whole square. And the reason for this step is actually pretty simple. That's because if this E term is 0 here, and if this E term is 0 here, then VA is equal to VB. In fact, we know that is what is going to happen in a completely inelastic collision. Both the objects are going to travel with the same velocity after that. So I can find out their k in this manner, and the expression which I will have after so I can maybe throw out this ma plus mb term here with the square in the denominator, and then I can probably take a LCM throughout, and I can also take something common. So I will have half taken common, and I will have ma ua square plus the second term will give me mb ub square, and the third term will give me ma square ua square plus mb square ub square plus 2ma mb ua ub, and this third term is divided by ma plus mb. And when you try to do the calculation, you will have, so half is here as it is. Then when you take the LCM, that is ma plus mb, so I'm going to put that ma plus mb in the denominator here anyways, ma plus mb. And when this ma goes with the first term, ma square ua square, and you know that this ma square ua square will be cancelled out, so gone. So I only have to worry about this mb with this ma. So I have got the first term as ma mb ua square plus, here you see that when this mb goes with this term here, then that mb square ub square and this mb square ub square will go off. So I have to only think about ma with this second term. So ma mb, and I have a ub square minus, because this minus will go over to this place, and you have 2 ma mb ua ub, 2 ma mb ua ub. And what happens? So this will give you can see that I can take MAMB and MAMB out of all the terms in the numerator, and MA plus MB can anyways be brought outside. So you have half times MAMB divided by MA plus MB, and what you have inside the bracket is UA square plus UB square minus 2 UA UB, which is UA minus UB whole square. Now whether you write that as a UA minus UB whole square or as a UB minus UA whole square, it doesn't matter, but I instinctively wrote that as a UA minus UB whole square, because I know that UA is more than UB, only then the collision happens. And this is the format of the loss of kinetic energy. So maybe you can keep this equation in mind, and you don't have to redo this entire calculation even with numbers. And there is another advantage to keeping this in mind. It's that this equation will keep on occurring again and again. Therefore, the total loss in kinetic energy, or the maximum loss in kinetic energy, is equal to maximum loss in kinetic energy is equal to half times MA MB divided by MA plus MB times UA minus UB whole square. And this term also has got a special significance. In some places, in some books, this is called reduced mass. So if you see that term, you should know that that is in fact this. So for a system of masses A and B, for a system of masses A and B, masses MA and MB, to find out certain properties of the system, and these may include if these two masses are attached with the help of a spring, and I'm interested in what is the time period of their oscillation, or maybe if I'm interested in the total angular momentum of maybe two stars which are going around their common center of mass or something. So then MA is one of the stars and MA is the other, MB is the other star. right? So in order to find out certain properties of a system of two masses, Ma and Mb, I sometimes use, not I, physicists, they sometimes use a thing called reduced mass, which is Ma Mb by Ma plus Mb, and we will get to see what is the importance of this term also in a detailed fashion, maybe in a later class. So for a system of masses Ma and Mb, to find out certain properties of the system, sometimes a term called reduced mass is used. And that reduced mass is, the symbol is sometimes mu reduced, or simply mu, or sometimes it is M reduced, whatever it is. And this is MaMb divided by Ma plus Mb. Now why is it called the reduced mass? That's because if you slightly change the way that this formula has been expressed, you will see that 1 by mu, and I'm just throwing away the subscript here, so 1 by mu is 1 by Ma plus 1 by Mb. And whenever you have an equation of this kind, then this term mu has to be less than the least of these terms. So mu has to be less than the minimum of Ma or Mb. In fact, if there were n terms here, Ma, Mb, Mc, Md, Me, and Mf, and so on, then mu would have been less than minimum of all those masses put. So you find out whatever is the least of them, and then you find out the value of mu. Maybe those of you who are interested in algebra a lot may want to prove this result, that if this is the format of a certain equation, then mu has to be less than Ma, it has to be less than Mb. But please keep that equation in mind for the maximum loss of kinetic energy in a perfectly inelastic collision of two masses in one dimension. So this is a very specific result, but useful nonetheless.